which is sort of a sad one. It's one of those good news, bad news situations. The good news is Monday is Labor Day, and it's a state holiday. So the bad news is we won't be meeting Monday. So get over it, okay, if you can.
I am pretty upset.
Huh?
I am pretty upset.
Yeah, I can tell. Okay, it shows. Okay, we're just about got projection showing up here, so let's pick up where. Now, why am I there? Okay. We got started on this, didn't we?
We were right at the definition of a cylinder.
Yeah.
Right after.
I thought we were getting ready to do example 1, and for some reason my slideshow didn't go there. Now maybe I did something wrong. We've done that and that and that. Here's example 1. Okay. All right, before we get started, any questions on anything we've done up till now? Okay. So it says, sketch the surface represented by each equation. Okay. Z is it. I hate sketching these things. Okay. And like I said, I don't do a good job of it. So let me get my pen set up. All right. Let that be my z-axis. That be my y-axis. That be my x-axis. Now, mine won't be nearly as pretty as the one in the book, I promise you. Okay? So, z is equal to y squared. How will that kind of look? Okay, that's going to be a parabola. I see y'all drawing it in the... Here, I'm going to put my negative axes here, so you sort of get an idea of 3 dimensions, even though I can't draw 3 dimensions very well. This would be just like y is equal to x squared. If that's the y-axis there, that would be this. So yeah, you'd have a parabola going up here and up here, okay? So, since x has no variability in this, your x's remain just whatever they are. So this comes out this way and goes back that way. At every point here, you come out forward and back, forward and back. You know, these go infinitely. So basically you have, picture a piece of sheet metal that's shaped out like a parabola, okay, in the YZ plane. And that's it, okay?
It doesn't go to x at all.
Yeah, the x's go infinitely along x and y, but there's no x dependence. Yeah, but yeah, that's why I say a piece of sheet metal. It goes infinitely. Okay, using this, that's my x, y, and z. Then it would be, I don't have a piece of sheet metal, so I'll use a thing. You know, if that is my parabola going from 0 up here on x, y plane, then it comes all the way out here. Yeah, infinitely in this way. And that way, yeah, every kind of way. Okay. So, there's that one. Ugly as my picture drawing may be. All right, let's clear that one. And, well, let's see. Let's not clear it all. Let's just clear all this scratch here so I don't have to redo my axes. All right, something like that. Okay, the B one then is z is equal to sine x. Okay, that's your sine function in the xz plane. Now, remember, sine starts at 0, 0, and when x is increasing, z will be increasing too. So it comes up to that, goes down. Pretty lousy rendition, okay? But, again, this time it will be a sine function in the xz plane, because y takes on any value at all. So there's the XZ plane, and it'll be a sine function going up and down like this, but y becomes infinitely in both all directions there, but that sine function is down there at the origin. And so at every point here you are going infinitely this way and that way, but following the curve here. You know, so it's that sheet that's waving like this. So, what would that be? A wave pool in this direction. Y infinitely in the y direction. Okay. Kind of see that one. Oh. I thought there was a C here. There's not. That last part says X is only going from 0 to 2 pi. So let's stop some of this mess before it gets going too far. You don't have anything back here because you don't have any negative x's. You're just this sheet here. And it, so your sheet does like this. And stops at 2 pi. Okay. So it's that wave like this. I can't call it to make it make any sense. But you see it in the book. Okay. All right. Now, that was all sort of just dealing with cylinders, cylindrical surfaces. Actually, the course description, I'm trying to think of the right word for it, said this course covers quadric surfaces. So we've been talking about cylindrical surfaces, which are fine, and I think it's worth talking about, but really here's what we should be talking about. Oh wait, I forgot. They're showing these, so let me erase all my stuff. So the first is the cylinder generating curve of z is equal to y squared, parabola in the yz plane, and there it is. Now they don't just say, or I don't think they meant, well maybe they did mean 0 to 2 pi on this one too, because they're showing that it ends at it starts at 12.
Well, I think it goes a little past into the negative. I think.
You see, this is only this one that has this. Yeah, this goes back past front and back. Now I see it, yeah. So yeah, this is a sheet that parabola, all the parabolas parallel to that along the x-axis, would be in that. So there was our first one. And the next one, the generating curve, is the sine curve in the xz plane. And there it is, but this one only goes from 0 to 2 pi. So it starts here, goes here, and stops here. So then put the sheet in there, infinitely going in y, plus or minus y, then just truncate it and show that part. There you have it. Okay. So there's how they were supposed to look. Okay. Now, quadric surfaces. This is where technically with this course begins. So we're not too far off. But the fourth basic type of surface, the first was the sphere, the second the plane, and the third was cylindrical surfaces. Here's the fourth basic type of surface, is a quadric surface. The quadric surfaces are three-dimensional analogs to the conic sections. Now, I think it's worthwhile to pause here and talk about what the conic sections are. Does anyone remember what the conic sections are? Now, frankly, I count a circle as part of the conic section, okay? And then a three-dimensional circle is a sphere, but they talked about that as if it was completely different, okay? So with those left out, then here are your other conic sections. I'll try to do them sort of in the order you probably did them. Probably you had parabolas first, okay? And parabola would be generally of the form like this, y, the simplest form, y is equal to x squared. Okay, that's the very simplest form. Get a little more complexity, you could say y is equal to ax squared. Okay, that allows you to make it fatter, thinner thing. You could also do something like y minus k is equal to x minus, or a times x minus h squared. That's sort of what they call the general form of a parabola. Okay, but in general, we'll just sort of leave it like that. One variable is to the first power, one variable to the second power. That's a parabola. Okay? That's just sort of the bottom line for that. All right. Now, I still am going back to this, to the circle. What is a circle again? Yeah, basic equation for a circle. That's it. Okay. Now, one form that I like for our purposes we're going to be doing, divide everything by r squared, and you have x. You can do it two ways. X squared over r squared plus y squared over r squared is equal to 1. Or x over r squared plus y over r squared is equal to 1. Okay, those are all forms of a circle. Okay, now, okay, I'm going to hold off of that for a minute. I'm just doing the conic sections. Now, do y'all remember why they were called conic sections anyway? Exactly. Now, think of a cone as being a complete cone. It meets at a point and it expands outward from that. And if it's a circular cone, then the cross-section of that would be a circle. Okay? And most of the time they are circular cones. And so that's how we get the circle in here. The parabola is if we cut a plane through this, just one part, the upper part of a cone, then you get a parabola. Okay. Now, if you take your cone and this time don't cut parallel to the, or perpendicular to the axis of the cone, that gives you a circle. But cut through the entire cone that way, and that gives you an ellipse. So the next one would be the ellipse. So this is the circle. Okay, this is sort of all over the place. The ellipse is very much like a circle, except for this. You have a major axis and a minor axis, so you have I'm going to use this form that they're showing down here. Ax squared plus bx, y squared is equal to, I'll put the minus j, to give you that same kind of form you have here. Now that's a rather strange rendition of it, but if you were to and j, yeah, so I get.
Why did you create the minus?
Well, I just did because I was trying to follow this and now I'm regretting it. Because in this case, j would have to be a negative number and minus j would have to be a positive number. So now I'm regretting I did. But I don't want to call it r because it's not exactly r. I was just trying to think of something else to do it. Let's just call it C, just to have something else to call it, a plus C. It's not that C down there, but, well, let's see, another letter, H-I-J, K. Let's just call it K. Capital K. Now, what I want to do is the same thing I did before, and divide by k, and you have ax squared over k plus by squared over k is equal to 1. Okay? Now, let's just give this k over a another name, like little a, and make k over b little b. Now notice I reverse them here, and therefore we have x squared over a plus y squared over b. Now that's equal to 1. Now, the only difference between a circle and an ellipse is the fact that the circle, both of your denominators are the same. And an ellipse, they're different. In fact, a circle is a special case of an ellipse. That's when these two are equal. Okay. So just to get in mind, this is what it is. Now, most of the time we'll call this a squared or b squared. So take it another step and do that. Okay. Rather than that equal a, make it a squared, make this one b squared. So now we have a squared and b squared. Squared, not b to the b power. Okay, that's your general form of an ellipse. Okay, much like a circle, and here's the key, both of these are squared. In a parabola, one squared, the other is not squared. In a circle, both are squared, a plus sign, both are plus signs, but your denominators are the same. In an ellipse, both are squared, the plus signs, both have plus signs, but now your denominators are different. Okay? But otherwise it looks just like a circle. All right. Now, the one other one, and this is one typically we don't do a lot, though you run into them, but we don't really name them very much, and this is called hyperbola. Okay? Now, there are some formal definitions to it, and I'm not want to get into those, but basically hyperbola, okay, picture your cones here. Now cut the cones with a plane that's parallel to the axis, okay? Parallel to the axis, okay? Then you have one going up like this and the other going down like this. That's a hyperbola, okay? So hyperbola is going to look like this. Or, one that we've done before is this one, 1 over x. Okay, that's a hyperbola. It always has a twin on the other side, but it's an inverse twin. Yeah, okay. It almost looks like an ellipse as if you move them this way and they connect, you know, but they really don't because there's a little bit of a point there. But, you know, it's kind of like that. So this is what your hyperbola looks like. Now, what's the deal with that one? It's a lot like an ellipse, only it's x squared over a squared minus y squared over b squared is equal to 1. That makes a hyperbola. Now, this would be this form. If you reverse those and had the minus on the other, that would be this form. And then if you did some cross products, you would have something that looks like that. Okay? Now, I wanted to just give you these forms to get them planted in your head. The first, the parabola, one's at the first power, the other's at the second power. A circle, both at second power, and the coefficients are the same. Okay? Identically the same. And pluses in between. An ellipse is a lot like that, but the coefficients are different with pluses in between. Hyperbola, one is plus and one is minus, but just like an ellipse, only one is positive, one negative. Now, these two could be the same or different, but you really can't tell. It doesn't make a big difference to it. Okay, so anyway, those are your 4 basic quadric surfaces. Now, technically, a line is also a quadric surface. If you do the cone and just go on the outer edge of a cone and cut like this, you get a line, right? Just the plane is along the edge of a cone. Then you're going to get a straight line. And that's what you get your plane from. And, so we already said the plane was a different form. It actually is a quadric surface as well. So a sphere is a quadric surface, a plane is a quadric surface, and it's only these cylinders that are not quadric surfaces, okay? But what we're talking about are these 4. Well, not circles anymore, but parabolas, hyperbolas, and ellipses, those 3. But we're going to put them together in a variety of ways. All right. So here then is your most generic form of your quadric surface. The equation of a quadric surface in space is a second-degree equation in 3 variables. It's a surface in space. When it's in space, you have to have 3 variables. The general form, and this is the most general form, you have some coefficient with your x squared term, the same or different coefficient with the y squared term, the same or different coefficient with the z squared term. Then you have your cross terms, the dxy, exz, fyz. And then you have your linear terms, gx, hy, iz, and then you have your constant term, j. And those are equal to 0. Okay? Now, if these 3, if all 3 of these are the same sign, generally plus, then that's going to be an ellipsoid. Okay? If one of these is minus and the others are plus, then this would form an ellipse if these were both plus, but then the minus would form a hyperbola, so that would be an elliptic hyperbola. Elliptic hyperbola. Well, wait. Ellipsoid. Hyperbola, and you could have either 1 or 2 sheets. They call them 1 or 2 sheets, so we'll get back to that. Now, let me talk about these cross terms. The cross terms mean your axis is not along one of your basic axes. In other words, your whole structure is tilted. That's what gives you the cross terms. We're not going to do any with the cross terms. Okay? Nothing. So we won't deal with any of those. Now, if you have one of these terms and 2 of these terms, what you have, and you have a plus in between these 2, both of these are plus, and this one's a linear. So say these 2 and the z, or these 2 and the y, and any form like that, that's going to be, these 2 with pluses will be an ellipse. One with the first power is going to be a parabola. That would be an elliptic paraboloid. Okay? Because remember, a parabola, 1 is to the first power and 1 to the second power. So if you have 1 of these to the first power, 2 to the second power, and there's a plus, both of those are pluses, then you have an ellipse from here, a parabola from there. Elliptic paraboloid. Okay? If you have a minus sign between these, that means you have a hyperbola. So this would be a hyperboloid, and one of them will be of 1 sheet and one of 2 sheets, and we'll explain that one later. Okay? Now, the one other is the elliptic cone. That is your original cone, but the cross-section is an ellipse, not a circle. So that would be an elliptic cone. And basically, missed one. Hyperbolic paraboloid. Paraboloid meaning one of these is to the first power, the other 2 or to the second power, but with a minus sign in between. Okay, 1 plus 1 minus, that would be a hyperbolic paraboloid. Elliptic paraboloid, 1 to the first power, 2 to the second power, these two have the same sign. That's the elliptic paraboloid. All three of these the same sign. They're all squared, ellipsoid. Okay? Elliptic cone, we'll get to that one and the hyperboloids. We'll get to that. That it's sort of hard to describe without seeing them. So, which I've been doing, and you haven't even seen them, but I'm just showing how the names correspond to what we were seeing before. All right. The intersection of a surface with a plane is called the trace of the surface in the plane. Okay? Now, we kind of did this with our cylindrical things, only they gave us basically the trace, and then you extended the surface. This time, we're going to have the surface, and they're going to give us a plane, and where that intersects, that's going to be called the trace of that surface in the plane. So to visualize the surface in space, it's helpful to determine its traces with some well-chosen planes. Now, what would be some well-chosen planes? The XY plane, the XZ plane, and the YZ plane. That would be well-chosen planes. Okay. Why don't they say that? But they don't. Okay. The traces of quadratic surfaces are conics. In other words, they're either parabolas, hyperbolas, ellipses, possibly a circle, but circle is just a special form of an ellipse, and lines. And those are also conics, by the way. Those traces, together with the standard form of the equation of each of the quadratic surfaces, are shown in the following table. So they show you first and then explain them later. Well, no, they're going you get the whole picture here. Okay, here's first our ellipsoid. Now remember what I said that was? An ellipse, both of them are square terms, but with different coefficients. Now we're going to let the coefficients, if you wanted to, be the same, because a sphere or a circle is a special form, just a restricted form of an ellipse. So they don't have to be different, but they can be. Okay, but all the variables are squared, and all the signs are the same, positive, and is equal to 1, just like we were getting before. Okay, now what makes this an ellipsoid? If you do your traces parallel to the XY plane here, every trace on the XY plane, you get an ellipse. The trace here is an ellipse. Here, 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 here. Everything parallel to the XY plane, you get an ellipse. Let's do one parallel to the XZ plane. You get an ellipse. You get an ellipse. You get an ellipse. They don't show these, but you do. You cut it this way. Let's cut it this way. The YZ plane. You get an ellipse, 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 ellipse. Everything's an ellipse. Okay? Now, here's how you represent those. If you're doing something parallel to the XY plane, let's take that one first. Let's just say the XY plane. You're doing that, but the XY plane, Z is equal to 0. Right? What do you have? You have an ellipse. That's exactly the form of an ellipse. And the XZ plane, Y is equal to 0. That's an ellipse. The YZ plane, X is equal to 0, that's an ellipse. Okay? Now what if they're not equal to 0, but something parallel, like X is, well, let's start with Z. Z is 1, not 0. Okay? Well, then this will be some number, 1 over c squared. Okay? Subtract that from 1. Okay? You still have a number, just a number, and this describes an ellipse. Now, if you don't like the fact that that's not a 1, divide by whatever it is and make it a 1. That just makes your denominator different. Okay? So therefore, everything you do to that, up to, you can't go past x equal a, because this is, by the way, you can't see the backside, but that's where that crosses the x-axis, and that's sort of a point. That's x equal minus a, this is x equal plus a. This is y is equal to minus b back here plus b here. Z is equal to minus c here plus c there. So of course you can't have any values beyond that, because if you went beyond a, you'd be out here somewhere. This would be something greater than 1, right? If x was greater than a, that would be greater than 1. And you're adding that to something that's positive and added to something else positive. No way you could get 1 out of it. So the only way you could be at this point right here, if the y and z were both 0, and of course they are at that point there, and then you're at x equal a. So that's the intersection. Minus a here, plus a here, minus b here, plus b here, minus c here, plus c here. Okay? Anywhere beyond that is not defined. Now, the ones on the axes, these are that. This just showed the ones parallel to the xy plane. They didn't show the parallel to the other planes. I don't know why, but they didn't. But here is the xz trace, the yz trace, and the xy trace. Those are the ones cut by the planes. But then anything above this is going to be an ellipse. Smaller, 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 smaller. This one's smaller, 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 smaller. This one's smaller, smaller, smaller. Yeah. You just get ellipses until you reach that point there, that and this and that. You stop and you can't go. Okay, now let's do a hyperboloid of one sheet. Now, a hyperboloid means that at least 2 of the traces are going to be hyperbolas. Okay? So the xz trace, that's going to be a hyperbola, where y is equal to 0. Or the yz trace is going to be a hyperbola, where x is equal to 0. So, here, there's where x equals 0, but y and z are not. That's going to be the origin here. There's the hyperbola there. In the yz plane, like this. Okay? In the xz plane, they're going to be like this. Okay? You can't see that backside. You can't look at this side. Notice here, when z is equal to 0, you get, or any multiple of z, you get ellipses. Okay? And sure enough, those traces are ellipses. Okay? So you can just mark out one of them, hyperbola, hyperbola, ellipse. So ellipses along z, hyperbolas along x and y.
Okay, any one can be negative as long as the other 2 are positive, right? It doesn't just have to be a straight up hyperboloid.
Okay.
Right? Like if x was negative.
If x is positive or negative, when you square it, it's going to be positive. All 3 of them are that way. So yeah, they're symmetric, positive or negative. If that's what you're asking, yeah, that's it. Is that what you're?
No, I was trying to see, take any one other than z and make it 0. I was trying to see what the trace would be.
Okay.
Just make y 0.
Okay, let's just cover that. And the trace here is a hyperbola. So when y is 0, you're in the xz plane. Here we are. There's this one, and there's the back one over here. Y isn't involved with it at all. We'll make x equals 0, and then here is the y on this side, there's the y on that side. It's sort of hard to see that. But that's not hyperbola. But make z equals 0, and you got an ellipse. Okay? And then anything going up or down from that would also be ellipses. And the fact that everything is squared means you got plus or minuses in both of these because you're squaring everything. Now we call this hyperboloid of one sheet because everything connected here. Okay? The axis of the hyperboloid corresponds to the variable whose coefficient is negative. I actually want to say it this way, whose coefficient is different, because you could make everything negative and then it would be positive, you know, so it's the one who's different. Okay. I think I said this earlier, but I didn't read this. The surface of the sphere, when you have an ellipsoid, it becomes a sphere when all three of these are the same. A equal B equals C, as long as they're not zero. Okay, if they're zero, you just have a point of origin. That's all. That's not very interesting. Okay. So, a hyperboloid of one sheet looks like that. What does a hyperboloid of two sheets look like? Well, then you have one positive and two negatives. Okay? Now, let's wipe out the y here. Here you have a hyperbola. Wipe out the x, or that equals 0. There you have a hyperbola. So you still have a hyperboloid, but this time, when you wipe out the z, you have something that can't happen. Z cannot equal 0. Right? Because this becomes negative, because x squared over a squared and y squared over b squared, everything's positive there, but you have a minus and minus that has to be negative, and two negatives can't add to be a positive. Okay? It just can't happen. So z cannot be 0. In fact, z can't be anything, has to be greater than c. So this is your minus c here, there's your plus c there. Okay? This makes a hyperboloid still. But now, again, your cross-section of this, as long as, okay, z can't be 0, obviously. But if z was greater than c, then this is a positive number. Okay? A number greater than 1, right? If z is greater than c, then this is a number greater than 1. Subtract it from this side, from 1, and you have a negative number. Well, then you have a negative, 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 multiply everything by plus 1, and you get hyperbola. You get an ellipse again, okay? And these traces up here, above and below z equals c, will be ellipses again, okay? So you have an ellipse when you're parallel to the xy plane and z is greater than c. Anything here or less than minus c, okay? So this makes a hyperboloid of two sheets. But let's do our traces this way. So here we'll go to this. The xy trace, it's this one, the xz trace is the one that starts here and goes down there. And the yz trace is here to over there, okay? They look a little bizarre here, but that's what they are. Same thing on the upper end too. Again, you get hyperbolas, okay? Here, however you do it. But you have ellipses above and below. Now, I don't know why they draw them like this. I guess there's a reason for it, but you can't see the hyperboles as well in this one as you do in that. Okay. Now, notice that all three of these first ones, ellipsoid and your hyperboloid of one sheet and two sheets, all have an equal 1 on this side. If that's an equal 0, that makes it a cone, okay? Now, the other thing you have to have is the signs just like your hyperboloid of one sheet, you see basically what you're doing. Take this thing and stretch it out and stretch it out and stretch it out until you have just one point there. That gives you an elliptic cone, because you've reduced that to 0 right here. Okay? And then if you think about it, if you made this a -1, that would be a plus, and a minus. And now you've made it 2 sheets. So basically, this is a weird way of thinking of it. This is a hyperboloid of one sheet, and as you let okay, this is some positive value, subtract off some negative value, you've got to get equal 1. Okay, so that when you imagine this shrinking and shrinking and shrinking in the middle, in other words, you're tightening your belt like crazy, until you get down to 0, then you get the elliptic cone. And then you keep tightening, just imagine this, and go to negative numbers, then you actually cut yourself in 2 and you go back to this kind of thing again. That's my strange way of looking at it. Now, what are your traces here then for your elliptic cone? Well, it's ellipses above and below, because when you wipe out the z, you have an ellipse, right? Okay, wipe out the, wait, I'm sorry, you don't have an ellipse. Well, yeah, you do. Well, wait. When you have z equals 0, you have a point, okay? That's all you've got, is that single point, 0, 0, 0. Z is equal to 0. But if z is equal to anything not 0, any constant not 0, then this is a negative number, because of the minus sign here. And if you add it to this side, you get a positive number. Well, that gives you, move this to this side, and that gives you ellipses here, above and below. Anytime z is anything other than 0. Z is equal to 0, everything's 0. But if z is anything other than 0, move it to this side and you got ellipses, up or down. All right. Well, what happens if you have this? Say y is equal to 0. Okay? Well, then you have, if you wanted to phrase it this way, c squared x squared plus a squared is equal to a squared. Let's say y is equal to 0. So that's disappeared. So now we have x squared over a squared minus z squared over c squared. I don't know why my pen is acting strange, is equal to 0. Well, let's multiply both sides by a squared c squared. And this gives you c squared x squared minus a squared z squared is equal to 0. Factor that, you got cx plus az times cx minus az is equal to 0. So you have x equal a over cz, or x equal, this is minus a over cz, equal positive a c over c. Okay, however you want to phrase it. And these are lines. These are, and that's what you get here. You get a line like this and a line like this, and when y is equal to 0, when x is equal to 0, you get a line like this and a line like that. It's hard to distinguish them because this is the y one. I think there's the x one. The corresponding y is this one, vaguely seen back here. Corresponding x is one vaguely seen there. But that's what you get. So these are these are lines, okay? Now, if you do traces this way, well, you get your hyperbolas again. I mean, this is just like your conic section. If you do a parallel trace to the YZ plane, that would be this one, then you get a hyperbola here and there, here, wherever you are. But if you're right on the axes, they just degrade down to straight lines. Okay? They don't say that here. Ellipses this way, hyperboles this way or that way. So that's your elliptic cone. Okay. Now okay. Your last two, your paraboloids. Be a paraboloid, one variable is to the first power, the other two to the second power. Okay? So when y is equal to 0, you have a parabola. When x is equal to 0, you have a parabola. Y is equal to 0 is a parabola. That's in the xz plane. Oh, that's this one. And when x is equal to 0, you're in the yz plane. That's that. Again, this is the xz plane. This one up here and goes up to there. And here's the YZ traces down here to there. Parabolas either way. What you have if you cross this way? Ellipses. Okay? So you have an ellipse when you're parallel, because when z is 0, or z is any number other than 0, when z is 0, you got a point, 0. But when z is any positive number, it can't be negative, can it? Because this is always positive, that's always positive. So this is always upright like this. That's an elliptic parabola. If c is any positive number, you have parabola, you have ellipses everywhere. Here, here. All these traces with z is any number other than 0. When z is 0, you have a point, 0, 0, 0. When z is negative, you have nothing, because it's positive on the right-hand side and negative on the left-hand side. It can't happen. So that's an elliptic parabola. Ellipses this way, parabolas every other way. However, if you have a minus sign in between here, this is a paraboloid because one variable is to the first power, the other two is to the second power. But if you have an opposite sign to this, that gives you a hyperbola. Okay? That's a parabola. That's a parabola. Now here's a key here. When x is 0, this is a parabola upward, opening up, because z and y opening up. And sure enough, there's your parabola that way, opening up. But when y is equal to 0 in the xz plane, now that one's opening down, because you have a minus x squared here, z is equal to minus x squared. So z goes negative here, z goes positive there. So you have this. I think back in Cal 2. No, we've still got to come to it. I get my calculus classes mixed up. We call this later, we're going to call it a saddle point. Y'all haven't called anything a saddle point yet. This sort of looks like a saddle, isn't it? The horse goes down the y-axis and your legs go across this way, so it's a saddle. Okay? So the saddle shape is a hyperbolic paraboloid. You have parabolas this way, and you have parabolas this way. Okay? But it's hyperbolas when you cut this way, because this is curving this way and that one's curving that way, so you have a hyperbola that way and that way. So parallel to the xy plane, you have hyperbola, and parallel to the xz plane and the yz plane, you have parabolae going in opposite directions.
Let's just say that again.
Okay.
The xz plane, you got parabolas.
Okay. So here's the form. 1 first power, 2 second power, opposite sign in between. Okay. Let's take the first power when it's constant. if it's 0, you're a single point in that 0. Okay, I think no. You actually have lines. It's hard to see them on here because if that was 0, then this could be factored just like we did before, and you have a cross section of lines. Okay, but if this is positive, then y has to be greater than x, or y over b has to be greater than x over a for this z to be positive. So then you're up here. Let's just deal with it. Okay, this gives you a parabola. When z is any number, you get other than 0, you get hyperbolas. Okay, because you have opposite sign between the two squares, and that's when z is constant. Up here, if you z is positive, they don't show it well here because they don't extend very far up. You see that would be a hyperbola on either side of that. When z is positive. When z is negative, you see this a lot better. Not on this one, but on this one. Pick some z negative here. There you have a hyperbola. They're going outward like this. Here they'd be going outward like that. So when z is any constant other than 0, you have hyperbola. So that's where the hyperboloid comes from. Hyperbolic comes from. Now, when x is 0 or some constant, then you have a parabola along the z-axis. Okay. Z is like your y, and this is like your x. Okay, so we're used to drawing them like this, and this would be opening upward in the YZ plane. The YZ plane. Yeah, and that's why you're opening upward in the YZ plane, and every one of these will be opening upward in the YZ plane, wherever you are. All those parabolas will be opening upward. But if this was 0 or a constant, then in the XZ plane, these parabolas are opening downward. And there you see that one, and this one would be 1, and that one would be 1. All these are opening downward in anything parallel to the XZ plane, and anything parallel to the YZ plane, these are opening upward. Like that. Okay. So you can tell by looking at that. And then when z is any constant other than 0, then these are hyperbolic. When y is greater than x, these are like that. And then, I may be saying it wrong. When z is positive, meaning y is greater than x, or y over b is greater than x over a, z is positive, your hyperbola are like this. Further up you get they're open like this, and when x over a is greater than y over b, then the z is negative, but the hyperbola, this one's open outward this way, and that one's open that way. So you can tell by just covering or putting equal to a constant, whichever one you want to be a constant. That forms the traces. These traces they show here, they're showing the minus x squares. That's what these are showing. Those are parabolas opening downward. You really only see, I guess all these are your parabolas opening upward here. What you don't see are your hyperbola in any direction, because they've only shown the traces like this and like this along the x and the y axis. They didn't show any traces on z. That's the only one to show on z. But you can see they just get bigger going this way, or facing the other way, going up this way, if you allow this to keep growing. So there's your elliptic paraboloid, which is, ellipses are your z traces, and your x and y planes are going to XZ plane and YZ plane are going to be parabolas everywhere. In your hyperbolic parabola, this is your saddle thing. Your traces along Z are always going to be parallel to the Z axis, well, perpendicular to the Z axis, which can be parallel to the XY plane. Those are always going to be hyperbolas. That's where the hyperbolic comes from. And then parallel to the XZ plane or the YZ plane, you get the parabolas, either opening upward or opening downward, depending on which plane you have. So those are the generic descriptions with the formulas. All right. Now, example 2, pages, by the way, 800 and 801 were exactly what we were just looking at on the slides. Example 2 is on page 802. Okay? It says, classify and sketch the surface and tell what it is. Okay, classify and sketch it. Okay, now the first thing I look at are your variables. And guess what? All the variables are squared. This is not a paraboloid of any nature whatsoever. Okay? Now, if all of the squared signs had been the same, that was going to be an ellipsoid. Okay? But here you have 2 positives and 1 negative. Okay? My gut reaction would tell me this is a hyperboloid because one is negative, the other 2 are positive. And that's true of hyperbola. And my gut reaction would say of 1 sheet. But the problem is, it's a plus 12 here. When you move over there, it becomes a minus. Okay, so let's see what happens. Let's do that first. This would be 4x squared minus 3y squared plus 12z squared is equal to minus 12. Right? Subtract 12 from both sides. Got it? Now, I want a 1 over here. So I'm going to divide this by minus 12, this by minus 12, this by minus 12, and this by minus 12. Right? Fair in most states. So this gives you x squared over, or minus x squared over 3, right? This is plus y squared over 4, and this is plus z squared over 1 is equal to 1. Okay? No. You let me get away with that? That's a negative. Very good. Okay. All right. Now, that tells me it's what? Okay. Has to be a hyperboloid. Yes. Because, you know, now, those together give you don't give you much of anything. Okay. If y were 0, that can't happen. Because this is negative, that's negative, and that's positive. Ain't going to happen. So y can't be 0. So this is obviously a hyperboloid because you've got opposites, you know, different signs here, and it has to be of 2 sheets because y can't be 0. So it's cut off there. So in the XZ planes, you have your 2 hyperboloids going that way. 2 sheets. Okay? To the wind. No, not that. Okay. So this looks like hyperboloid of 2 sheets. Okay? The dead giveaway is y can't be 0. Because then you have negative, negative, equal positive. Can't happen! So y can never be 0. So it's got to be, and you got hyperboloids all over the place, so it can't be. Now, if y is large enough, okay, in other words, greater than 2, because then this term would be greater than 1, when you subtract that from that side, you get a negative number, and then you have negatives everywhere, so that you can just multiply through by -1. You have positive everywhere, and that gives you ellipses. So you have ellipses above and below, right, I'm sorry, y-axis. This way, 2 sheets now, one's negative, one's positive. And those are ellipses that you cut that way, but every other cut is going to be, that's going to be a hyperbola, that's going to be a hyperbola. So hyperbola, 2 sheets. Does that make sense? Just looking at it. Did I want to sketch it? Oh, no, I don't. Well, I'll try. Okay. So, I hate sketching these things. Okay, again, X, Y, and Z. Okay, you know Y can't be 0, so let's extend the X-axis, the Y-axis, and the Z-axis. Y can't be 0, so you've got your ellipses here. Well, let's see what it is. Y at plus and minus 2, I think it is. That's where they begin. Okay? Because only defined here. So and I can't draw worth of 2. Okay, that's kind of what they look like. Is that close enough?
Yeah.
Okay. All right.
Exactly.
What's that?
It's pretty much exactly
Okay.
what it looks.
All right. You're being very kind. Okay. Not going to get you any more points. So. No. Okay. Okay. All right. That's what it is. Hyperboloid, because the signs are different, of 2 sheets, because there's one of those variables can never be 0. Okay. All right. Okay. Let me get my ugliness out of here. Well, not all of me, I'll stay, but okay. So what we're going to do, begin by writing the equation in standard form. There's the original equation. Okay. Subtract 12, okay. They divide by the constant. This is a weird way to do it. And they divide by minus 12, which if you move the 12 over, it'd be obviously why you divided by negative 12. But it's not as obvious here, but it does work. Okay? And that gives you this form. I like to go on and put the z over 1 just so it looks right. Okay? And now why in the world they reverse the direction? X and the Y's. But it did at first. I said, wait a minute, but then I saw they changed the variables. Okay, so you can conclude that the surface is a hyperboloid of 2 sheets with the y-axis being its axis. The reason y-axis is the axis, that can't be 0, because that would make this side negative and that side positive. It can't happen. Okay, that's my easy way of seeing it. There may be better ways to do it, but that to me nails it. Okay. To sketch the graph of the surface, it helps to find the traces on the coordinate planes. Now, I didn't bother doing that, but when z is equal to 0, you have hyperboles. Okay? I went the wrong way. And when y is equal to 0, it can't happen, okay? No trace, because y can't be 0. Right-hand side is positive, left-hand side is negative. Can't happen, okay? And then the yz trace, where x is equal to 0, you get hyperbola again. So hyperbola is in 2 directions, no trace in the other direction. Okay? That's what you got. You see, when y is equal to 0, you get no trace at all. X equals 0, then you get hyperboles this way, and that way you can't really see it very easily. And z is equal to 0, you get your hyperboles that way. That helps draw it. Okay. They're skipping example 3. So let's try to do example 3 here. Shame on them, all they say is, oh no, they say classify and sketch the surface. Okay, x minus y squared minus 4z squared is equal to 0. Okay. All right. What would you do first? One variable is different, isn't it? First power. Let's isolate it. X is equal to y squared plus 4z squared, right? Isolate the linear variable, right? Got it? Okay. Now, one observation. Plus in between here. That tells me x can never be negative. Because this is always positive, that's always positive, sum of two positives is positive. X cannot be negative. Well, the only thing that opens only one way is going to be a paraboloid. And this gives it, makes it certain. When x is anything, when x is 0, these two have to be 0. Okay, no way around that. But when x is any positive value, then what you have is ellipses, right? So, and then one variable to the first power, the other to the second power, it's got to be parabolas. So you have an elliptic paraboloid. Exactly. Exactly. Okay? Now, we classified it. That's the easy part, in my mind anyway. The sketching of it. Okay? I don't draw my axes well. I don't draw anything well. X, Y, Z. Okay? Sounds like my computer's making little noises. I don't know what they're for. Okay. Now, the ellipses are when x is any constant, not 0, any positive constant. So basically, and your it's a little different in this form, but your major axis is your y-axis, your minor axis is the z-axis. So these are going to be ellipses that do something like this. Bigger and bigger, smaller and smaller. So here's your ellipses, ellipsoid, something like that. I'm not yeah, your ellipsoids are coming out the x-axis. Mine are terrible, terrible, absolutely awful. And the but that's what you got. Maybe it would help to do a line like that. I don't know. I can't make it look any better. Okay. But you see, generally, that's what you got. It's opening this way, the x being the axis of that.
I got the drawing right for the wrong reasons.
What's that?
I got the drawing right for the wrong reasons. Trying to figure out how to get it right. I got it on the x-axis, but then I'm trying to, I was thinking about that was 2 sheets. Now I'm going, how did I do that?
No. That's,
Let me go back to that definition.
Oh, I didn't write it down. Okay. This is a paraboloid, an elliptic paraboloid.
Right.
Okay, I should have written that first.
That's right. It's got to be the x-axis.
The one that's
Can't be negative. Can't be negative.
right, and the one that is to the first power, that's always going to be the axis that it's symmetric about. Okay, so that was example 3. Now, they said they weren't going to do this, and then they turned around and did it. No, maybe I said they weren't going to do it. I was wrong. Let's see. Where does the next pick up? I can't remember what slide is next. That was the previous one. Oh, surfaces of revolution. So we've still got example 4 to go. So let's do example 4 here. Okay. Let me erase my scratch. And here will be example 4. Classify and sketch the surface. X squared plus 2y squared plus z squared minus 4x plus 4y minus 2z plus 3 is equal to 0. Okay, now guess what I said before? I forgot to say anything about this. I said the cross terms, xz's, yz's, xy's, they're not going to do any of those because those are the things that make it tilt, and various things like this. What I forgot to say was what happens when you have your quadratic terms and linear terms, okay? That means you have say again?
Is this more easy way to complete the square?
Yes, okay? That's exactly what we were going to be doing with this. And this is because this is an offset. You no longer have your center at the origin. If you didn't have any linear terms here, then your center is always at the origin. But if you have the linear terms with a corresponding quadratic term, exactly what Bill said, you have to complete the square. So get your x's together, your y's together, and your z's together. So if all 3 of your variables have quadratic terms, but then you also have linear terms in 1 or more of those, you have an offset. You're not going to be centered at the origin. If all 3 of your terms were quadratic with no linear terms there, everything's centered at the origin. And if you think about all those things we did before were always at the origin, not this one. So get your x's together. X squared minus 4x blank plus 2y squared plus 4y blank, the book doesn't do this, obnoxious blanks, plus z squared minus 2z blank is equal to -3. Now, all I've done is rearrange and left some blanks and move the constant to the other side, right? Because these 2 terms are exactly those 2. These 2 are exactly those 2. And these 2 are exactly those 2. I just took the +3 and moved it to the other side. I got -3. Just as Bill enthusiastically suggested, we go on to complete the squares of every one of these. Okay, pretty much. Okay? So let's complete the square of this one. How do we complete the square of the first 2? Half of -4 is -2. Square it and you get +4. Well, I just changed the whole equation, didn't I? Unless I do a +4 over here as well. Now it's still equal, right? Okay. Now, I'm going to pause for a moment here. And while I'm pausing, I'm going to go on and write what that is. That's x minus 2 squared. Just so I won't have to carry around as many numbers. But what I'm going to do next is pull out the 2, factor out the first term, and that gives us a y squared plus 2y. Agreed? Yay or nay? For those 2, I want to pull out the 2. Okay, so I haven't changed anything. Okay, this one is going to be, oh, I left off my obnoxious blank. Forgive me. Okay, I knew not what I was doing. Okay, plus, let's go on and complete the square for the z's while we're here. What would that be? Z squared minus 2z. Anybody? It's not. Yeah. Z squared minus 2z. Complete the square for that one. Half of minus 2 is minus 1. Square that, you get plus 1. Well, I just changed the formula, but I'm going to add another. This is a plus 1 that we had, plus another 1. Okay? Now let's get to our y term. Okay? This is going to be x minus 2 squared plus 2 times, let's complete the square of that one. Half of 2 is 1. Squared is 1. So this gives me y squared plus 2y plus 1. Okay, but pay attention. We didn't just add a 1. We added a 2 times 1 because this 2 is outside that parenthesis. Well, 2 times 1 is 2, so we've got to add it over here. And here we had a 2. 1 plus 1 is 2. High-level math today. 2 plus another 2. Okay. And then what is this squared there? That's the same as z minus 1 squared. Now, I don't know if I've told you all this before. Probably not. Well, I can't remember. As soon as I complete the square here, when I say half of this term here is a minus 2, I usually come down here and write the minus 2 in here because that's always what goes here. Then you square that and you add it here, you do that. And here, half of this was minus 1. Write down the minus 1 right there. It's always going to be there. This one, half of this is plus 1. So this one's going to be x minus 2 squared plus 2 times y plus 1 squared plus z minus 1 squared is equal to 4. Right? I hope I did it right. Now let's divide everything by 4. Okay, now I'm going to come up to the top and rewrite what we've got there. X minus 2 squared over 2 squared. I'm going to write it that way. Plus, here 2 will go into 4 twice. Y plus 1 squared over root 2 squared. Now I'm doing this for a reason. Okay, plus z minus 1 over 2 squared. Z minus 2 squared over 2 squared is equal to 1. Okay. Now, the reason I did it that way is your center of this ellipse is going to be 2 minus 1, 1. Oh, it's an ellipsoid. How do I know it's ellipsoid? Square terms all positive ellipses. Got it? Got to be ellipses. The center is going to be 2 minus 1, 1. Okay? Because when x equal 2, this becomes a 0. When y is equal 1, that becomes a 0. When z is equal to, y becomes a minus 1, that's a 0. When z becomes a plus 1, that becomes a 0. So that's your center. 2 minus 1, 1. Okay. Now, that's the center of the ellipse. Okay. The x-axis is going to go 2 to the left, 2 to the positive and 2 to the negative of that. That's what that tells you. On the y-axis, it goes square root of 2 positive and negative. That will give you the terminals there, and the z will go plus or minus 2 of that. So basically in the YXZ plane, these are going to be circles, not, they are ellipses, but they're going to be circles. In the XY and the YZ, they're going to be ellipses, because this is your minor axis, those are your major axes. So that's, it says classify, so we've classified. It's going to be an ellipsoid with center at 2, -1, 1. Okay? And you could put what the minor and major axes are going to be, but I'll worry about that later. In fact, I'm going to let me make sure I drew it right first. Yeah. Good. Okay, so I'm going to erase. Why didn't I? Well, I'm going to have to erase it by hand because I don't have room to graph it otherwise. Anyone need any of this before I erase it? Everybody got it? Okay. All right. Now, here's my ugly little axes, X, Y, and Z, and ugly little negative axes too. Okay. And let's tick off a few points. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Positive 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Positive 1, 2, 3, 4, 5. Negative 1, 2, 3, 4. I hope I don't need any more. Okay. Let's find the center. That's +2 on X, -1 on Y, and +1 on Z. So there's your center of this ellipsoid. Something like that. Okay? Now, let's parallel an x-axis here. Let's parallel a y-axis here. And parallel a z-axis here. Okay. Now, the x is going 2 plus and minus from 2, so that's going out 1, 2 from here and 1, 2 from there. So that's going to be our vertex on the x-axis. Your y's are going 1, 2, 1, 2. It's going 1.414, that's square root of 2. So that's going to be something about like that. So there's the vertices on the y-axis, and on the z-axis it's going up and down 1. No. Up and down 2, sorry. Yeah. Okay, so 1, 2, 1, 2. So there are your points there. So here is your trace on the y-axis, on the new y-axis, and this is an ugly, ugly trace. Okay, here's the trace on the x-z-axis. That's supposed to be a circle on this one, but because of my weirdly shaped thing, that's a circle that way. And on the YZ, it's going to be this way. So that's kind of the ellipse. It's pretty ugly, isn't it?
Yeah.
Okay, you didn't have to agree so quickly. Okay. All right. But if you look in the book, we're not too far off of that. Okay. Ugly though it may be. Okay. So, all right. Got it? Okay. So there is how you do, if it's not centered at the origin, complete the squares. Now that only works when you have only quadratic terms and linear terms. You can't have any of the cross terms. The cross terms are going to skew it, twist it, bend it some way, and those you talk about hard to draw. Oh my goodness, next to impossible.
But what I'm saying, suppose now that you had a assembly equation with only one had cross terms.
Only one had a cross term?
Yeah.
Okay.
Is that what you're saying?
No, the really bad is when all three have cross terms.
Okay.
X, Y, Y, Z, X, Z. Then you have things tilted in every axis.
That's why we have computers.
Yes, you got that right. That's where graphing, whatever you call it, packages, that's what makes them worth their money, okay? I don't know how much they cost, but they're worth it. Okay. There is a technology, a 3D graphing utility can help you visualize surface, and it shows a couple of theirs. I don't have one to demonstrate it on, so if you happen to have one, go for it. Now, surfaces of revolution, frankly, we kind of did these in Cal 2, didn't we? Not us, Bill and I did, but so I want to sort of go through these kind of quickly because
Just like revolving it around an axis?
yeah, exactly. Yeah. So surface of revolution. The fifth type of surface you will study is the surface of revolution. So we had spheres, planes, what was the other one? Cylinders, right? And then quadratic surfaces, that was 4. Here's the fifth type, is surfaces of revolution. Okay, you'll now look at a procedure for finding a surface of revolution's equation. This we probably didn't do. Consider the graph of the radius function, y is equal to r of z. This is meaning that your y is your dependent variable, z is your independent variable, and your radius is a function of that z. So that's going to be in the yz plane, obviously. When the graph is revolved around the z-axis, it forms a surface of revolution. Now, why do we say z-axis? That's the independent variable. So we're going to revolve around that. It forms a surface of revolution, as shown here. The trace of the surface in the plane z is equal to z0 is a circle whose radius is r of z0. Okay? And that's what they're showing here. If you're going around the independent variable z, that's your axis of revolution, then any trace parallel to the xz plane, where z is equal to some constant, z0 here, then this is going to give you a circle, because that's what you're doing. You're revolving it around the circle. Okay? That's going to be a circle whose radius is z0. And his equation is x squared plus y squared, the circle formula, is equal to r, which is r of z0 squared. X squared plus y squared equals r squared. This r depends on that value of z that you chose, z0. Replacing z0 with z produces an equation that's valid for all values of z, and that would just be y is equal to that r of z. Or your equation would be x squared plus y squared is equal to r of z squared. Okay? So in a similar manner, you can obtain equations of surfaces of revolution for the other two axes. The results are summarized here. If the graph is a radius of a radius function r is revolved around one of the coordinate axes, then the equation of the resulting surface of revolution has one of the forms listed below. If it's revolved around the x-axis, then The x is going to be involved with r, and this will be y squared plus z squared is equal to that r of x squared. Okay? Revolves around the y-axis, that's going to deal with the r, so x squared plus z squared is equal to r of y squared. And it revolves around the z-axis, then x squared plus y squared is equal to r of z squared. Those are your three formulas that you would come up with. Okay? Got it? All right, so here's example 5. Find an equation for the surface of revolution formed by revolving the graph of y is equal to 1 over z about the z-axis. Okay? Okay? Well, this is going to be your radius function, so your r of z is going to be 1 over z. Okay? And once you know that, then you say x squared plus y squared is equal to 1 over z squared. Okay? I think this is all there is to it. You could rewrite this, though I don't know exactly why, x squared z squared plus y squared z squared is equal to 1. I don't think they do that. They just leave it in this form right here. They put 1 over z in parentheses squared. It doesn't matter. Okay. But you got it? All right. Now, the second is the graph of 9x squared is equal to y cubed, and you want to graph or revolve that around the y-axis. So you want to find x as a function of y, because notice your you want whatever your axis is, that's what you want your variables in. So you want this to be a function of y. So let's solve this. First thing we're going to do, divide by 9. I can't divide by 9. Okay, and then take, okay, x squared is equal to y cubed over 9, and take a square root of both sides. X is equal to the square root of y cubed over 3. Square root of 9 is 3. So there's your r function as a function of y, because you're going about the y-axis. Okay, so what do you have? X squared plus z squared is equal to, when you square that, you have y cubed over 9. Okay? According to everything I've seen, that's how they would leave it, but you could write this as 9x squared plus 9z squared is equal to y cubed. That's another way you could write it. They left it, like I said, x squared plus z squared equal to 1/9 y cubed. They wrote it 1/9 y cubed. Either one's fine. Okay. Okay. So, let me clear my writing out of here and see if they are going to do anything any differently. They clear it. An equation for the surface of revolution formed by revolving the graph of y is equal to 1 over z about the z-axis. Now notice about the z-axis. We already have this as a function of z, So this will be x squared plus y squared is equal to r of z. There is your r of z. But you're going to square that, so that would make it x squared plus y squared is equal to 1 over z squared. And that's why they wrote it in that form. I wrote it 1 over z squared, which is the same thing. Okay? To find an equation for the surface formed by revolving the graph of 9x squared equals 3y equals y cubed. Read. About the y-axis, solve for x in terms of y. Because if you're solving about the y-axis, you want your variable, your r variable in terms of y. So we want it in terms of y, so solve for x in terms of y. That's going to be 1/3 y to the 3/2 power. I didn't write it that way, but that's a perfectly good way to write it. Now what you're going to wind up doing is squaring. This is your r of y, and then you're going to write your x squared plus z squared is equal to this thing squared, which would be x squared plus z squared is equal to that thing squared, which will be 1/9 y cubed. Okay, they show you squaring it first, and how they show every step 1/9 y cubed. Okay, that's your equation of the surface. All right, and there's the graph of it. Looks like a big megaphone, doesn't it, or something like that? Okay, well, I need to have a little bit of my ear because I'm hard of hearing. Okay. Now, there was that generating curve that they had, 9x squared equal y cubed. Fine. You couldn't prove it by me that they didn't do it wrong, but or right. I have no clue. Now that's all they're going to do. The next part, they talk about finding the generating curve. Are y'all particularly anxious to do that? That's not part of your course description. So I'm ready to move on if y'all are okay with it. Huh? Okay.
Just talk about it for a minute.
What's that?
Just talk about it for a minute.
Yeah. You say you want to talk about it?
Yeah, just
Yeah. Okay.
I'm not gonna hold the class, but
Right. Okay. It's kind of going, there's a part of it I want to say backwards from what we did before. It's not exactly, well, let's see. Here they gave the generating curve, and then you found the equation. Now we're going to give you an equation, says find the generating curve and the axis of revolution, which it depends on one, depends on the other two. So here's what they're going to do. Here's a surface of revolution. Okay, here's a surface. X squared plus 3y squared plus z squared is equal to 9. Okay? Now first, that does make sense, because everything on the left-hand side is positive, the right-hand side is positive. So that does, it looks like something that would work. If that had been a minus 9 over there, say hang it up, there's nothing going to give you that, okay? Because everything on the left is positive, the right has to be positive, and it is. Okay, now, you have three, there's the axis, there is the surface, okay? Now you can either have x squared plus y squared is equal to some, they call it r of z squared. Okay? Or you could have a x squared plus z squared is equal to some r of y squared. Okay? Or you could have some y squared plus z squared is some r of x.
Okay, you can stop there, because we over.
Oh, we're over time?
Well,
Okay, I'm sorry.
when do we?
155. Oh, we're way over, aren't we? Sorry about that. Yeah, okay. Okay, do you want to come back to this or go start in the next section?
Well, we can just start the next section.
Okay. Okay, let me just go over homework exercises here then. I would do all of 5 through 10, but you'll find the answers for the odds of 5 through 9 are in the back and at calcchat.com. Okay. Then do either 11 or 13. They're both at CalcChat. 11's at CalcView. Do any of the odds 15 to 25. They're all at CalcChat. 17's at CalcView. You can explore doing 27 or 29. They're both at CalcChat. Should be. And then I'm not going to hold you to doing surfaces of revolution. If you want to do any of the rest of those odds, you certainly could. And all right, we'll pick up next time. Oh, we're not going to do 11.7, which is cylindrical and spherical coordinates. That wasn't in our course description, so I wasn't planning to. I can do a quick slideshow if you want to do that, just so you're familiar with them. Yay or nay? No?
I'm not going to.
Okay. Then,
Let's go ahead and tell you.
okay. Well, actually, I might do a quick slideshow just to show you what they look like. In case you ever do need them, you'll at least seen them before. But we'll do it. So let me go on and mark that as a slideshow. But you're not going to be responsible for this on the test. Okay? I just want you to see how the basics of them. Okay, you won't be assigned any exercises for them. And this 11.6, just the quadric surface part, is all you're responsible for on the test. Now we'll pick up, after we do the slideshow on 11.7, we'll pick up with chapter 12. That's where the bulk of the next test is coming from. Okay? So let me end this. That was supposed to be an hour and 40-minute class. We went an hour.